Hello, my name is Benjamin, and welcome to our talk about ReDMArk bypassing RDMA security mechanisms. So this is a joint work between me, Konstantin Taranov, and our professors Adrian Perrick and Thorsten Höfler. So let's start off by defining what we actually mean by RDMA network. So RDMA stands for Remote Direct Memory Access. So on this slide, we see a high-performance system. It could be any kind of data center system. And then we see a node complex here with the gray background. So on this node, we are receiving packets, and those packets are actually going through an RDMA-capable network interface card. So the key about RDMA is that the CPU is not involved actually in receiving the packets and putting them into main memory. So this is all done by the RDMA NIC. Eventually, those packets will be consumed by the CPU. But until that point, it's just offloaded basically to the network card. So RDMA, as of deployed today, is able to do that at a very high speed. So if you consider a Mellanox Connectix 6 card, we receive roughly one packet every 2.5 nanoseconds. And soon, with 400G available, you'll get like one packet roughly every nanosecond, which is massive speed. So processing a packet at those speeds is actually problematic and complex for the host. And this has led to the deployment of RDMA NICs as very highly specialized packet processing engines that deposit packets at this rate into the main memory without involving the CPU at all. So RDMA has recently got a lot of attention, not only in research, but also in like regular data center applications. And today, many data center providers just deploy RDMA systems for performance reasons. RDMA itself is actually designed for performance, so it offers lower latency and higher bandwidth, and also lower CPU utilization. But what about vulnerabilities, exploits, and mitigation for those? So in this talk today, we'll talk about those aspects of RDMA. So in ReDMArk, we actually consider 4 different adversary models. And we found 10 vulnerabilities. And using those, we implemented 6 different attacks and also provide 8 different mitigations that either fully mitigate the attack or increase the attack complexity. So as mentioned, we consider 4 different attack models. So we numbered those from T1 to T4. So considering T1, the attacker would be a regular and non-regular end host, and it can connect to an RDMA service and issue messages over this connection. And then if we consider T2, here the attacker has compromised an end host, and he can try to fabricate and inject messages into existing connections. Then T3 would be an in-network attacker, so it would be on path, and in addition to T2, it can also eavesdrop and modify packets that are bypassing. Then T4 is a bit special. Here we actually consider a malware-based attack and use RDMA for data exfiltration. So in today's talk, we'll mainly consider attacker T2 and T3. So here is the form of an RDMA packet. So first we have the routing header, which is similar to an IP header. Then we have the base transport header, which would be similar to like a TCP header, and include endpoint matching information that is actually required by the endpoint. For example, match it to the right connection, put it into the right buffer, and so on. Then in addition to regular packets, we have also an RDMA header, which contains the target virtual address, the memory key, which is an access token, and also the data length. And in the end, we have 2 checksums. So if packet arrives, we check these checksums, and if they match, yeah, it's all good. Otherwise, we have corrupt packets. Then in the second step, we do the QPN matching, so we actually match the packet to an existing connection. And if it doesn't exist, then we can also discard the packet. Then for PSN, this is like a sequence number. So we do ordering and detecting of duplicate packets. Then in the fourth step, we match the R key and check whether it's valid or not. And in the end, we do the vertical rest translation to find the correct target for our packet. Interestingly, the first three checks are silent to the application. So if something goes wrong, the application will never hear about those packets at all. And in the case of 4 and 5, there will be a connection error. So we'll see later how we can exploit this feature. So for packet injection, we actually need to bypass the first three checks. So packet injection can happen, for example, using RDMA Send. And then for unauthorized access, we need also the check 4 and 5. So this would be like an RDMA read. So let's see, what happens if the first check. So the problem is that neither encryption or authentication are used in today's RDMA protocols. The CRC checksums are well known, have known seeds and polynomials, so they can be easily computed by an adversary, because those are just designed for packet integrity checks, so whether any kind of bit flip happened in the network. So for the second step, this QPN matching, we found out that, although QPN numbers are 24 bits, and which would result in like 17 million possible QPNs, in practice, they're allocated sequentially. So this means knowing a certain QPN number, predicting preceding or subsequent QPNs is actually trivial. So we analyzed a bunch of different devices from Broadcom and also Mellanox, different generation, as well as a RDMA implementation in software called RoCE, and for all of those, the QPN number allocation was sequential. In the third step, we do this PSN matching. So the packet sequence number is also 24 bits, but it can be selected by the entity that creates an RDMA connection upon creating this connection. So in RDMA, there are typically two ways of doing that, establishing connection, and one is using IB verbs, and the other one is using the RDMA connection manager. So if a software uses the RDMA connection manager, it will actually assign a random PSN to the connection. But establishing the connection using IB verbs leaves the option of choosing this PSN actually to the developer. And we analyzed the different open source RDMA systems, and then they tend to prefer IB verbs with a static PSN over the connection manager, probably out of simplicity. So now that we actually bypass the first three checks, we are able to inject packets using RDMA Send. So we implemented a proof of concept injection tool, and we can actually inject up to 1.6 million packets per second using a Mellanox ConnectX-5 card. This is done purely in software, and so it takes us roughly 11 seconds to enumerate the full 24-bit packet sequence number. We also have some interesting observations. So if we inject RDMA packets with an invalid PSN, it doesn't break the connection at all. So in case its duplicate packet is just dropped and also acknowledged back to the sender. So this means for us, we can actually silently replace packets. And if we inject exactly 2 to the power of 24 packets, the PSN counter wraps around, and we can even hide the attack from the application. To prevent packet injection, there are a number of different options. So the first would be just to use encryption or authentication. One option is called sRDMA. And then the second option would be to randomize the QPN number, and we provide an algorithm for this in the paper. The third step would be to randomize the PSN, which is kind of trivial. And more modern hardwares, for example, the Mellanox ConnectX-5, they offer hardware counters that are actually able to detect such attacks. So in the next step, we ask ourselves how we can actually misuse packet injection for an attack. So we can misuse packet injection for denial of service. So our approach would be basically, packets that pass the first 3 checks but contain some protocol errors. They can actually force an existing queue pair into an error state. So using injection of packets, we can actually break existing QP connection by forcing them into an error state. As you've seen on previous slides, we can inject up to 1.6 million packets per second. So in case we have a known packet sequence numbers, we can scan 1.6 million different connections per second and actually disconnect them. And in the second case, when we have an unknown PSN, it takes like roughly 11 seconds to enumerate the entire PSN. So yeah, it's very important to actually have some randomness in how we select the queue pair number, because it's very, very important to increase the attack complexity for packet injection. So the example here is with a victim with 1,000 different RDMA connections, and with our tool, we would actually be able to break one of those connections in 48 hours. All right, so in the fourth step, we actually match these R keys, right? And R keys are just 32-bit access control tokens. But unfortunately, the R key generation is highly predictable. We found that it's like less than 3 bits of entropy in this R key generation process. We also found other different problems. For example, there was some static initialization for key generation, which means the network interface card generated the same keys even after rebooting the server. And we also found that often the same protection domain is used for all queue pairs. So it basically allows access to memory even without impersonation using any queue pair connection. And also, if multiple applications share the same network interface card, they also share the same key generator state. So basically, one application is able to predict the keys of the other application just by getting its own key. And in the fifth step, we want to bypass this address check. So this means we actually need to guess what are valid addresses. And typically, virtual addresses are 64 bits, but in Linux we only use 48 bits. And then if the developers tend to use this page-aligned memory for performance, it's only 36 bits. But what really helps here is actually that objects, in case of RDMA, are actually allocated in consecutive addresses with respect to a random address. So this means once we know a valid address of our buffer, for example, it's very easy to predict where other buffers of other applications might be. So one example is InfiniSwap. So InfiniSwap is a remote swapping device for Linux, and it uses this POSIX memline call in a loop to allocate buffers of 1 gigabyte. So basically, if you're an attacker, it's very easy to predict the position of these newly allocated buffers compared to our buffer. And to mitigate such attacks, we can also use sRDMA again. And in this paper, they propose some extended memory protection. This would help here. Also, randomizing this R key would be of great value. And in the paper, we provide an algorithm for randomization of R keys. Then also, the addresses of those buffers could be randomized. This would make this fifth step way more secure. And also, protection domains should only be shared between trusted connection and not between all connections on the same host. And in the fifth, we can also use this type 2 memory windows, which actually restrict access to a certain memory window to a single QPN.
Okay, hello everyone. I'm Konstantin and I will present the second part of the talk. So I will talk about additional attacks, which are not related to injection or impersonation. So mainly we will try to answer the question whether any client, just normal client of your RDMA system, can harm it. So the first question, whether a client can DOS an RDMA system. So it's actually possible. The first thing that we looked at is the number of open connections. So as you know, in the protocol, we have limit on the number of QPair numbers we can have. So it's 2 to the power of 24. So in theory, a client could just occupy all these connections, and then nobody could connect to the system. And you can think that this is the big number, but actually when we checked multiple systems and different devices, this number was much lower. So this QP limit on average was around 64,000. And this number was usually limited by the driver. So the driver have more stricter limit on the number of possible connections. So of course, a simple mitigation to that attack is just to count how many connections a remote endpoint opened. So the next attack also can be performed by any client. And here an attacker can exploit the fact that all these one-sided operations, they're performed silently. So it means they're performed by the NIC, but the OS doesn't get notified about it. And in that case, an attacker can inject a lot of packets that could flood the system, and then it would consume resources of the RNIC. So first, I'd like to talk about the mitigation. Of course, as a mitigation, applications could block RDMA writes and RDMA reads operations. Or for detection, they could also use hardware counters, which can show how many packets has been processed. So now I'd like to jump to the experiment. So in this experiment, we created a system at the client, and we measure latency and bandwidth observed by client. And then we launch attackers which inject the traffic over the system. So for the first experiment, we measured latency and throughput of RDMA reads. In our setup, attackers were injecting RDMA write packets. As RDMA writes are always enabled by default, and RDMA writes are usually always supported by the systems. So as you can see on the first graph on the left, when we had a one attacker, then the latency measurement did not change a lot. However, when we increase the number of attackers, we could increase the latency of RDMA read by an order of magnitude. And this is quite severe for applications which are latency sensitive, like consensus protocol or transactions protocol. Also, we performed a similar experiment for the throughput, and as you can see, we managed to drop the throughput also by an order of magnitude. In the second experiment, we measured latency and throughput of RDMA writes. We could see a similar observation. So one attacker wasn't able to significantly affect performance of a client. However, again, once we get 8 attackers, we could increase the latency by a factor of 10. For throughput, however, we could only observe 2x reduction in throughput. So now I'd like to jump to this attack, which is in another threat model. So this is threat model T4. Here we assume that the attacker has an ability to change an application of a victim. So it could inject code. And actually it could inject the code which could establish a covert channel with a machine which is owned by an attacker. If you think about it, when you have your server or your application running on a server, and if the server has this accelerator, it can be quite dangerous, as the accelerator has access to your memory, it has access to the DRAM, which should be just enabled by the application. So the attacker could inject the code which would enable the access to the RNIC, and as a result, the attacker could actually use silent RDMA reads and scan the memory of the victim's application. Of course, as a mitigation, the applications should have code attestation, but right now I'd like to show a small demo. So in this demo, we have two machines connected to each other through InfiniBand. So on the left side, we will run an attacker application, and on the right, victim application. So first, in the same network, attacker starts application which waits for a connection, and that opens a server at the given IP address. And then we'd like to look at the application of the victim. So as you can see, we just added this preload function, so which is injected by the attacker. And the code of the victim is simple. So victim just allocates memory for a secret and reads secrets from the standard input. And we hope that attacker would be able to catch this secret. So as you can see, once the victim started the application connected to the attacker starts scanning the memory. So at the beginning, there is some garbage, but once the victim enters the password, attacker was able to catch it. As you can see, the attacker was able to catch all the passwords of the victim. Also, we print the messages every few seconds just to have more readable output. Right now, I'd like to show you the code. So actually what is in this preload function. So if you're familiar with IB verbs, so this is just simple code for establishing connection and for registering memory and sending this information to the attacker. I'd like to show you the pseudocode of this function, of this preload function. So first, this preload establishes a connection, then it allocates memory, and then registers it for RDMA read access. And then it sends this information to the attacker. And then we free the buffer. And here we use two main facts. First fact, if we register memory and then deallocate it, it's still RDMA accessible. And the second fact, malloc is deterministic function, and we can always predict what happens in the code. So here we use the fact that if a client uses malloc of fixed size, if we deallocate the same size right before this malloc, we would get exactly the same address as the client will get later, as the victim's application will get later. So we use these two facts and could able to find the memory address of the password. So now I'd like to briefly talk about mitigation schemes. So of course, why we could inject the packets as there is no secure channel supported by RDMA networks. That's why applications should use IPsec over RoCE, which was recently introduced, or they could use SRDMA. This is our proposal for secure communication for InfiniBand-based architecture. So I'd like to invite you to read the paper. Then we show that QPN are not random. And actually, there is a simple software solution to that. Applications could create connections. They could create QPR connections and do not connect them. So they would get a connection ID assigned is QPN, but they will be just in initial state. So application could allocate randomly all these QPR connections and then connect them later on demand. So as a result, QPR numbers will be random for the clients. For the PSN randomness, we already mentioned that RDMA Connection Manager helps you to get random PSN numbers. And of course, I would recommend to use RDMA Connection Manager, but unfortunately, it's not secure. So everything RDMA Connection Manager does, it exchanges messages in plain text. So the best secure way, if you'd like to have secure connection establishment, you should do it on your own and then use it in the native InfiniBand interface, which does not exchange messages. It just creates the connections from the scratch on the endpoint without any messages exchanged. Similar to the randomness of QPN, we offer an algorithm which would help application to randomize R keys. For this, applications could just register some anchor memory. So they could allocate one page and then register it. And then they would get new R keys. And then they could sample from these R keys random R key. And then when they need to register a new memory, they could just re-register it and remap it to the new address. When you use IBV rerec call, you actually preserve R key, but you could change translation. That would help applications to have random R keys right now without the wait for the firmware update from the vendors. Of course, we also recommend applications to use multiple PDs, so never share connections. Untrusted connections should never share PDs. Plus, applications can use memory windows type 2, which are more secure as they offer binding memory to the connections. Plus, I'd like also invite you to read about crypto-based memory protection offered by RDMA. Finally, for the memory randomness, the application developers should avoid simple or obvious memory allocations when they allocate memory in the loop. Again, malloc and all these allocation algorithms, they're deterministic. You always can predict the address if you know the pattern of the application. So as you can see, we analyzed 6 different applications and all of them were vulnerable to this attack. So the attacker could always guess the location of the memory. And as an example, I'd like to explain what was in the RAM cloud. So probably you know RAM cloud doesn't use one-sided RDMA, but in the implementation, they did 2 main mistakes. So the first mistake that even they don't use one-sided RDMA, they will register memory for remote access. And the second thing, they don't send clients information about the memory as clients are supposed to use send and receive API. But for the performance reason, the developers decided to implement memory allocator, which starts memory allocation from the address of 40 million. So it means all the applications always know that all the RAM cloud nodes, they have client's data starting from this address. So as a result, the client could just find the R key using vulnerabilities which we mentioned in the paper and write and corrupt the memory of other clients. On that, I'd like to finish the talk. So ReDMArk is available open source. And if you have questions, please contact me or Benjamin. We are happy to answer your questions offline.